Hello, my name is Christian. I work as an IT consultant and developer for Knowit ObjectNet in Oslo, Norway. That is one of my photos. Low-light photography is a hobby of mine, and I just couldn't resist using my favorite image of streaming clouds here. This talk is about real-world experience from 2 customer projects I've been working on for the last 2.5 years. I'm currently looking for new projects with related fields, so if you have any interesting leads, please talk to me or contact Knowit ObjectNet about it. I've chosen a fairly pretentious title for my presentation, and it is rather long, but I hope you'll find it interesting. I know I do. So, what is the Industrial Internet of Things? It's quite probable that you're doing Industrial IoT if your IoT gateway doesn't look like the one to the left, but more like the one in the middle, or like a server blade, and is connected to something similar to the PLC, Programmable Logic Controller, to the right. Some of the photos I use are photographed by people working for Arando, or they are licensed for commercial use by Arando. I worked on projects there for 2 years and learnt a lot. Super place to work. The photos are used with permission. Other parts of my presentation relates to work I'm currently finishing up for PowerTech Engineering. I've been really lucky with my customer projects lately. The PowerTech images are used with permission. I should also mention that I use some photos released for commercial use by pixabay.com. I've worked with data streams from various sources, like smart buildings, pumps, generators, large diesel engines, pile drivers and spinning machines. The main challenge is all about the amount of data, and the fact that the data streams never end. You would need a data rate of minimum 1 measurement per minute from multiple sensors in order to detect the need for maintenance of pumps and generators for the oil industry. You might have to increase that to every second or so if you're working with engines or production equipment with higher rotational speed. One of the storage solutions I've been working on is currently receiving more than 20,000 sensor measurements per hour, 500,000 values per day, from a single smart building equipped with 5,400 sensors. It used to be 125,000 sensor measurements per hour, that is 3 million values per day, but we tweaked the sample rates based on customer needs and requirements. We also worked on local buffering mechanisms with micro-batching. The storage mechanism is almost idling now, ready for scale-out, enabling thousands of smart buildings to be connected in the near future. A single surface-mounted microphone will deliver between 40,000 and 200,000 samples per second to those who want to explore sound. By then you might have to fast Fourier transform the audio and run machine learning on the dominant frequencies and their amplitudes. A trained machine learning model could potentially run on an edge device close to the microphone instead of in the cloud. Also, video streams are interesting, given that you're able to separate anomalies from what's normal, preferably before you waste lots of bandwidth. There is never one single machine to monitor, always a number of them. Multiple buildings, one or more factories, a fleet of ships, all of an operator's subsea oil pipelines. That kind of scale. Industrial IoT is never implemented just for fun. There needs to be real, reasonably short-term economic value involved. Alternatively, it needs to be about fulfilling new environmental requirements. IoT data may need to be buffered for multiple weeks if your sensors and equipment are at sea. They may need to be transferred to the cloud when the ship is in harbor, or the data may be brought to shore on removable disks. IoT data streams don't have to be transmitted in real time to provide value, though sometimes you'll want to perform at least parts of the processing on site, for example optimization of fuel consumption for tankers and tugboats, or detection of anomalies for subsea oil pumps. It's perfectly possible to run trained machine learning algorithms on quite primitive equipment, like relatives of Raspberry Pi or a small rugged PC, maybe directly on your IoT gateway, that in some cases can be as powerful as any server blade. You also won't need a lot of machines to be able to deploy a reasonably redundant Kubernetes cluster, even if your architectural choices become much more limited than they would have been with a cloud provider. You may actually find a local cloud, like Azure Stack, on an oil rig, but I wish you luck with getting certifications and permission to deploy your own software to one of those. Your stream processing gets really simple if all you need to do is call an already trained machine learning algorithm. You provide for receiving all sensor measurements relevant to the algorithm using sensible data rates for the purpose, and feed that to the model as the data arrives. You may also want to store all the data as cheaply as possible in HDFS, a data lake, or in blob storage, in a way that makes it easy to separate both equipment and days for the next time you require data to retrain the algorithm. This type of data stream filtering is easy to implement in Kafka or Azure Stream Analytics, and you can perfectly well do this in addition to other stream processing. But most customers of Industrial IoT require something more tangible in addition to just a callable algorithm that detects something fancy. They often require dashboards that show how production goes in real time with fancy graphs, multiple dimensions, color-coded performance and downtime. These dashboards may have low practical utility beyond showing them off at board meetings or talking about them to people you want to impress, but they can on the other hand be extremely hard to implement, particularly when your customer also wants parameterizable reports that can compare current and historic periods of time. The rest of my presentation will be about architectural choices geared towards solving these kinds of tasks. The key to create fast updating charts and reports is to store the underlying data on a format that can be easily combined into the desired result, with a resolution that doesn't require too much work per recalculation. These precalculations are typically called aggregations. The aggregated precalculations must be stored somewhere. This storage space is often termed warm storage because it provides high availability access to pre-processed data with a granularity suited for presentation purposes. This is opposed to cold storage, which typically stores all the data in original form, which usually requires a certain amount of time and effort to retrieve and process before use. If you store the count of values, the minimum value, the maximum value, the sum of values and the sum of squares of each value for a set of time intervals, then you can easily calculate the average, standard deviation, variance, sum, count, minimum and maximum for any combination of the time intervals using simple formulas. Average and standard deviation can be used to display normal distribution bell curves for values within the combined intervals. Thus, the aggregates still retain quite a bit of information about the original raw values. As a data scientist, you'll often find that just observing the values that stream by doesn't give you enough context to perform complex calculations. You may need a cache of recent data or a place to store partial pre-calculations, aggregates, and potentially the output of machine learning models, typically for use in dashboards and interactive parameterized reports. Warm storage is often used by data science applications and algorithms that call machine learning models in order to quickly retrieve sufficient sensor values and state changes from streaming data. Warm storage data may typically be used to detect anomalies, generate warnings, or calculate key performance indicators that add insight and value to streaming data for customers. Those KPIs are often aggregated to minute, 10-minute, hour, or day averages, and stored back into warm storage with a longer retention period to facilitate reuse by further calculations. The stored partial aggregates may also be used for presentation purposes, typically by dashboards or in some cases reports with selectable parameters. Thus, optimal retention periods may vary quite a bit between tenants and use cases. A good warm storage needs flexible low-latency querying and filtering for multiple tags simultaneously. It must be able to relate to hierarchical tag IDs, representing an asset hierarchy for flexible matching and filtering. It needs storage support for KPIs and aggregates calculated from within algorithms that may optionally call machine learning models. It needs query support for seamlessly mixing calculated data, sensor data, and state changes. An often overlooked topic is that warm storage should be opt-out by default, not opt-in. Every insert into warm storage will cost you a little bit of performance, storage space, and memory space for indexes, before it's removed as obsolete. All data that is scanned through as part of index scans during queries will also cost you a little bit of I/O, memory, and CPU every time you run a query. Tenants that have no intention to use warm storage should not have their data stored there. Neither should tags that will never be retrieved from warm storage. The first rule of warm storage is, don't store data you won't need. Excess data affects the performance of retrieving data you want, costs more money, and brings you closer to a need for scaling out. A good warm storage should have a Python wrapper to make it easier to use from data science projects. If you're using warm storage in a resource-restricted environment, the APIs should behave the same as in a cloud environment. Most of the existing stream processors are very focused on performing MapReduce in real time, on never-ending data streams. That's obviously immensely powerful, and you can do lots of interesting things to data streams that way. But it's overkill and unnecessarily complicated if all you're looking for is some aggregations, calculations of a few key performance indicators, and a bunch of simplistic alarm triggers. The exception seems to be Kafka streams, KSQL for Kafka and Apache Samza. All of those lets you consume Kafka topics in order to send derived streams back into Kafka, in the shape of new topics or tables. Kafka, which primarily is sort of a cloud-sized message bus on steroids, is interesting in many ways, but also quite large and complex. It actually feels a bit daunting to install and configure and use Kafka for the first time. You just know there's a huge learning curve ahead before you'll be able to achieve a mature solution. Additionally, Kafka wouldn't be my first choice to store large amounts of sensor data for a long time, even though Flux DB, the database engine for Kafka K-tables, is a good one. Confluent provides a managed Kafka cloud service which works with Google Cloud, Azure and Amazon Web Services. Let's keep Kafka and particularly KSQL with K-tables in the back of our minds. In the meantime, let's have a look at what time series databases can offer us. Flux DB is open source and probably the fastest time series database on the market. It's capable of running on reasonably powered edge devices. Flux DB uses a text-based format called a line protocol for handling data, but has a SQL-like query language. Flux DB utilizes a completely static data structure centered around the timestamp, with attached value fields and metadata strings called a tag set. The metadata are indexed and you can search using both metadata and time ranges within each time series. Flux DB doesn't support updates, but you can delete specific data between two timestamps or drop an entire time series. You can also overwrite the value fields if you take care to use exactly the same timestamp and tag set. That's usually almost as good as being able to update. Flux DB performance is closely coupled to cardinality, which is all about how many metadata tags that need to be indexed and that are scanned during queries. All queries must be bounded within a time range to avoid performance crisis. Flux DB supports automatic aggregation and calculation of derived values by means of so-called continuous queries. Deletion of all data can be handled automatically by retention policies. Both of these mechanisms cost a little bit of performance when they are used. Flux DB have implemented their own storage engine written in Go. What scares me a bit is the number of storage on support forums about people who wonder how they lost their InfluxDB data. There's a managed InfluxDB service available on cloud.influxdata.com. Timescale DB is an extension to the PostgreSQL relational database. Both are open source. Timescale DB splits tables into partitions called chunks, based on a predefined time interval, or automatically as time series data are written to each hypertable. These chunks are really tables themselves, and have individual indexes. Only a few of these smaller indexes need to stay in memory most of the time. This as good as eliminates the major problem with utilizing relational databases for time series data, provided that all your queries confine themselves to reading from a low number of chunks, and that each chunk contains no more than 25 to 50 million rows. Queries, inserts, updates and deletes across chunks are handled transparently with standard PostgreSQL syntax. Dropping entire chunks at a time is a very effective way of implementing retention limits to get rid of expired data. It's necessary to use connection pooling if you want to use Timescale DB from a REST API. You also need to control the connection timeout and the statement timeouts. You can write only to the master node if you're using a highly available PostgreSQL cluster like for instance Patroni, but you can scale reading by sending queries to all the replicated slave nodes. Timescale DB exists as a managed service on both timescaledb.com cloud and as managed PostgreSQL for Azure. You can scale both Timescale DB and Flux DB by sending unrelated time series data, for instance belonging to different customers, to separate database clusters. This kind of scale-out is commonly called sharding. Timescale DB and Flux DB could both handle long-term storage and aggregate storage responsibilities in low-resource environments, like when your customer doesn't want to use cloud services, or when you want to analyze sensor data close to the relevant equipment for connectivity or reduced latency reasons. This is commonly called edge computing or running on edge devices. Cassandra is a distributed cloud storage service based on Google Bigtable technology. It needs to run on multiple machines and isn't capable of running on a single node edge devices in a sensible way. Cassandra has many features that make it particularly well suited for handling time series data. Cassandra utilizes a masterless architecture with no single point of failure and scales almost linearly to a large number of machines, VMs or pods, as the need for storage space grows. Data is stored compressed and redundantly with multiple copies across several nodes. You should avoid using Cassandra on top of redundant disk volumes. That would simply increase the storage requirements and lower the performance. Cassandra is optimized for write performance over query speed, updatability, and deletes. The query language is a lot like SQL and supports complex data structures like lists, sets, maps, JSON objects, and combinations of these column types. Cassandra is not a relational database and doesn't use joins. All Cassandra queries and commands should be performed asynchronously. Data that belongs together is partitioned on the same node to improve query performance. It might be a good idea to store multiple copies of data, instead of creating secondary indexes whenever you need to retrieve that same data using different access patterns. On paper, HBase and OpenTSDB, a dedicated time series database built on top of HBase, seem like good alternatives to Cassandra. Cassandra is, however, more complex to configure, maintain, and code for than Cassandra. Another interesting alternative is ScyllaDB, which claims to be a self-optimizing Cassandra, re-implemented in C# in order to achieve performance gains. ScyllaDB is rather new and doesn't yet have the huge community support that Cassandra enjoys. Storage is cheap. Store IoT data the way you want to read it. Feel free to store multiple copies in alternate ways. That's called query-driven design. Joins and transactions are as good as irrelevant for IoT data streams. They don't change after they've been sent, and joins cost performance. You may also need multiple aggregation intervals for different purposes. Preferably aggregate each granularity lazily after you are comfortable that the underlying data have arrived, and not every single time relevant data arrives. Utilizing mechanisms like time-to-live indexes or time-to-live tombstoning can affect performance surprisingly easily. Try to find a way to utilize deletion of chunks or other partitions whenever your storage mechanism supports that. It can be very inefficient to delete expired data by searching through or recompressing huge amounts of data. Sometimes it's far better to simply leave expired data where they are, rather than spending time and resources cleaning up. It may in some cases also give you cheaper cloud provider bills. You can implement your own partitioning by writing data to separate tables, depending on timestamps within predefined intervals, and then drop the oldest tables when all their data have expired. The disadvantage is that you must create and drop tables dynamically, and may need to read from more than one of the tables at a time. This could be a way to implement short-term buffer efficiently in Cassandra, which is able to handle several millions of inserts per second when scaled out. Always strive to use native database types for your index columns. Native types are often much more compact than string representations and are scanned using pure binary comparisons. Definitely never using case-insensitive or culture-dependent collations, which can happen if you're not careful about how you define string columns. A native UUID is stored in 16 bytes and can be compared as two 64-bit integers. A UUID string is 36 bytes long, plus the length marker, and is hopefully compared in a case-sensitive, ordinal way. A native timestamp with time zone is stored in 8 bytes and can be compared as one 64-bit integer. This seems like a small thing, and I know we're not supposed to pre-optimize, but it's really about the innermost of inner loops. An industrial IoT storage solution surely performs billions of index comparisons every day. The indexes are read from disk into memory cache, often called the buffer pool, where the index blocks are traversed, and hopefully remain until the next time each index block needs to be checked, unless another index block needed the same memory space more urgently. Eventually you can get buffer pool trashing, where index blocks are read from storage into memory over and over because the buffer pool is too small for the most frequently used index blocks. You can expand the size of the buffer pool until it's constrained by the memory installed in the machine, or maybe more typically allocated to the virtual machine. But another thing that really helps is when the index column values are compact and simple to compare for every row. This maps directly to less index data to read from storage and room for more index data in the same buffer pool. You should also strive to avoid large index range scans by writing your queries carefully and by storing data as you want to access it, optionally using multiple copies. Database systems like Cassandra support batching of commands on an API and protocol level, and can execute batches asynchronously on multiple nodes. That's particularly effective when an entire batch uses the same partition key. But batching can be supported even when using SQL, when you know the syntax. Utilize this to write multiple values using the same command, so that the number of network round trips is reduced. You'll spend much less time waiting for network latency. I encourage the use of arrays when writing your own REST APIs. Use arrays actively for inserting multiple values and for retrieving sets of series in the same method call. This makes life easier for data scientists and reduces the aggregated network latency when using the API. Reducing latency for things you do often improves performance. You should strive to send and receive multiple elements per call when you're using queues for IoT data. Most queue implementations support this, and utilizing it can reduce the need to scale out significantly. Handling each sensor measurement typically represents very little processing. Thus, you might as well receive a number of them at a time to avoid the aggregated network latency of fetching them one by one. Utilizing micro-batching all the way through, including synchronizing sample timestamps or buffering upstream for a few seconds, can have a profound impact on performance. I've seen 10,000 sample values written to the short-term buffer, with a full copy to the long-term storage, registering 4,000 new scheduled aggregations and updating 12,000 statistic log entries complete in 3 seconds as a single microbatch. It's likely that handling each sample value would take around 100 milliseconds if those same 10,000 sample values were to be processed individually on the same storage system. Some of it would definitely be handled asynchronously, but we could easily end up at around 500 seconds total. More than 8 minutes of processing time for those same 10,000 sample values that microbatching handled in 3 seconds. You could certainly scale out as an alternative and process more in parallel, but scale out costs money in the shape of larger bills from your cloud provider. Not utilizing microbatching may at one point limit the total throughput you'll be able to achieve, and the difference between using it and not can be dramatic. The biggest problem with microbatching is the fact that your microbatch may fail as a unit, even when it contains many perfectly okay sampled values. You need to have good exception handling and logging upstream, including the ability to queue or buffer data for a while, in order to counteract this. Kafka or an IoT hub that supports MQTT or AMQP may be close to perfect for this kind of queuing. Validation issues with any specific sample value and its metadata should ideally never fail the entire microbatch. It should log a detailed description of what went wrong, including relevant series ID, timestamp, and sample value. to a log that's constantly monitored. Then the problematic sample data may either be sanitized or discarded, depending on the severity of the problem. Processing the rest of the microbatch should continue as if nothing extraordinary happened. We had an issue where some sensors started sending the string NAN, not a number, instead of a floating point voltage. That caused the post body to be incompatible with the JSON type schema. Our validation code never even ran, and we had to look for the problem in the failed JSON body of the upstream site service. We found it on line 86,442 of a 107,636 line long, seemingly valid JSON snippet. It took us around 15 minutes to spot that. Detailed error messages are pure gold. That microbatch was over 2.5 megabytes and completed in 2 seconds when the NANs were replaced with null. We have since changed that JSON type to string and do our own validation to check for invalid numbers, but there can easily be more problems similar to that. This is a quite typical architecture for warm storage. A small number of persistent stores with different access patterns. A few processes that run continuously. One or more APIs that implement REST methods that can be invoked using HTTPS. You authenticate to receive time-limited access tokens that provide a set of basic permissions. You utilize HTTPS Keep Alive to achieve persistent connections and reduce the effort spent performing cryptographic handshakes. Communication with the storage services should utilize SSL, and you'll need to provide certificates for both database servers and the API implementations. Whether you'll need to configure encryption of storage service data files or not is dependent on how paranoid you or your customers are. It might cost you quite a bit of performance. It's advantageous to choose managed storage services whenever they're available. That is because someone else takes responsibility for actively managing the service, like setting it up with a sensible initial configuration, upgrading it with security patches, providing redundancy and resilience against failure, scaling the service without losing data, providing reliable backup options, and tedious stuff like that. This obviously costs money, and you might choose to take the responsibility yourself in exchange for lower monthly cloud provider expenses. You should probably choose a fully tested operator Helm chart to manage your pods if you choose to deploy your storage services on top of Kubernetes. Google awesome Kubernetes operators in the wild for inspiration. We've been using a highly available PostgreSQL cluster called Patroni, deployed on top of Kubernetes on OpenStack using the Zalando Postgres operator. You have a pod with one master PostgreSQL node, which does both writes and reads, and 3 pods with slave PostgreSQL nodes, which replicate the master but can also be used for reads. These pods are separated between 2 data centers after an enlightening incident a while back, where an entire data center lost power. Most of our services went down with it, even though they were supposed to be redundant. Did you realize that you might need to use a geo-redundant Docker image repository for Kubernetes to be able to start new pods? Anyway, these Patroni PostgreSQL nodes utilize etcd and the Raft protocol for leader election and failover, whenever the Patroni health monitor decides that the current leader isn't sufficiently healthy. Then one of the slaves will be elected as the new leader, and the old leader will be demoted to a slave. This happens once in a while. The PostgreSQL client libraries don't really know about leaders and failovers, so whenever we see an exception that the current PostgreSQL session is read-only, we'll terminate the process immediately, so that Kubernetes restarts the pod and we can get new connections to the current leader, utilizing Kubernetes service selectors. That works. The old leader, however, wasn't demoted until a few tenths of a second after the new leader was elected, and for those tenths of a second, the old leader happily received streaming IoT data through the existing open connections, which sometimes creates an alternate timeline, which prevents the old leader from joining the new leader as a slave. One solution is to copy the additional data to the new leader and re-init the old leader. Handling stuff like this transparently is sort of what you're paying for when you utilize a managed cloud service. When you host your own storage solution, it may become your, or rather my, responsibility to fix it. The short-term buffer is used to calculate aggregates from raw data and as data source for any key performance indicators or derived data calculations that may be needed. The short-term buffer will contain every single measure inserted through the storage API, but truncated to a retention period typically between 48 and 72 hours, depending on how many aggregations that are scheduled but not yet processed. Measures with identical timestamps down to the microsecond level, belonging to the same time series, will be treated as duplicates by the short-term buffer. Thus, only one of the simultaneous measures will be stored and aggregated. This duplicate removal may be handy when working with the quite common at least once delivery guarantees of some IoT systems. Measures arriving outside of the current retention period might be written to long-term storage if required, but will be too late for the short-term buffer, will not be aggregated, and not be included in any performance calculations. The access pattern for the short-term buffer is very write-heavy, with quite a few sequential reads limited by time ranges. All short-term buffer data expires and potentially needs to be truncated on at least a daily basis. This access pattern doesn't fit Cassandra or HBase very well, because of the transient nature of the data. Queues are commonly described as a Cassandra anti-pattern unless you can delete data by truncating entire tables. The short-term buffer access pattern fits much better with Timescale DB, which extends the PostgreSQL relational database with automatic time partitioning of tables. The retention policies of Flux DB would also match the short-term buffer well. There might be other good choices too, but regular relational SQL databases and quite a few NoSQL databases like MongoDB would soon expire performance problems because of indexes that grow to unmanageable sizes and would need to be swapped in and out of memory a lot. We could utilize multiple side-by-side instances of Timescale DB or InfluxDB to handle the short-term buffers and aggregation schedule queues for different independent customers or for non-related groups of equipment. This kind of scale-out is commonly called sharding. The long-term storage database is for storing raw data that can't or shouldn't be aggregated, for example state changes or alarms and their context, or structured JSON documents. It's a good idea not to store metadata like time series properties or asset hierarchy information in the long-term storage directly, mostly because it grows huge and may become cumbersome to maintain over time. You want as few updates as possible. Thus, there is an advantage to using GUIDs for identifying time series in the long-term storage. Then you let the time series properties handle asset hierarchy searches and metadata versus GUID mapping. This also helps with anonymizing data in the long-term storage, which is a good thing and helps separate unrelated data. The long-term storage database will see a huge amount of writes, some sequential reads typically caused by dashboards, user interfaces or reporting. There might not be a need for updates except for deleting expired data, which might represent a significant performance overhead for some database systems. This access pattern fits very well with large-scale distributed storage services like Cassandra, HBase or OpenTSDB. Timescale DB or InfluxDB might be better choices if you're restricted to an edge device or a low-resource environment, and know that the amount of data that needs to be processed and stored will remain manageable. The long-term storage database should not be used to store high-frequency time series, as this over time will consume a lot of storage space and represents data that might be difficult to process in a close-to-real-time scenario, which is what the storage architecture is designed for. If you want batch processing or want to train models on huge amounts of raw data, it would be better to filter the streaming data in a sensible way, creating a retrieval path that lets you easily get to the right block of data and then append it into a cheap redundant distributed file system or in blob storage, rather than clogging it up a long-term storage database that simultaneously attends to real-time responsibilities. This time of stream filtering is very easy to implement with Kafka or Azure Stream Analytics and can easily be performed in addition to warm storage. The aggregate storage is for storing numeric aggregations. Each interval stores the count, minimum, maximum, sum, and sum of squares for each measure in the interval. From these we can additionally infer average, standard deviance and variance for every multiple of the base interval duration. Just like with long-term storage, it's a good idea not to store metadata like time series properties or asset hierarchy information in the aggregate storage directly. UIDs for time series IDs keeps the number of updates low and separates unrelated data in a good way. Sensible interval durations are typically between 1 minute and 24 hours. Interval durations must be selected with care for each type of time series, as they represent the compromise between precision and storage size, which is basically what decides how fast you'll be able to retrieve or process a result or display a relevant graph. For example, aggregating room temperatures in office buildings to 24-hour intervals is too coarse, because climate control systems usually shut down at night and commonly during evenings. 1-hour intervals are probably just right, because that gives you 8 or 9 separate aggregates during working hours, and each interval includes average temperature, maximums, standard deviation, and variance. 1-minute intervals would, on the other hand, represent wasted storage space and unnecessary processing overhead, because you constantly need to retrieve a lot of them just to average them after retrieval. The main disadvantage of going above 24 hours is that your intervals will start to mix workdays and holidays, and in some cases a few of your intervals may become differently sized, for instance around New Year's Day or at the end of months. Inconsistencies like that will increase the variance of the aggregates and you'll lose precision. It's usually a better solution to keep each 24-hour interval separate, and rather average them each time you need statistics for a larger interval. The aggregate storage database will have an access pattern quite similar to the long-term storage database, dominated by writes but with more sequential reads within time ranges. It should probably be stored in the same data storage solution as the long-term storage database. We'll probably need to use client code in the API in order to combine aggregates, because not all database systems are able to group sums over time intervals. Sometimes it makes sense to store 2 base intervals separately. Say you aggregate the power consumption of a climate control system to 10-minute intervals in order to facilitate day-to-day comparison graphs. That translates to 144 combinable aggregates per day, 1008 per week, and 52,560 per year. You would have to retrieve and combine 262,800 aggregates for each climate control system in order to show a graph that compares power consumption for the last 5 years. But if you store aggregates for an additional 24-hour base interval, you would only need to retrieve and combine 1,825 aggregates for those 5 years. That makes a huge performance improvement, and your end user won't have to wait so long to get his results. The aggregation schedule helps to implement delayed or lazy computation of aggregates. It appears to be part of the Internet's nature that IoT data can arrive delayed, in the wrong order, sometimes even with duplicate blocks of data, if a TCP/IP packet containing a confirmation incidentally never returns to the original sender. This seems surprisingly common when sending IoT data out of China, even when using SSL. Although common messaging protocols such as MQTT and AMQP both define exactly one's reception, not all implementations allow you to enable this, possibly because of performance considerations. Anyway, the gist is that every time a time series value arrives with a timestamp within the aggregation interval, it's likely that a similar value may arrive soon. This is reinforced by the fact that TCP/IP itself is packet-based, and that protocols such as MQTT and AMQP and we ourselves prefer micro-batching. Therefore, we calculate a new delayed aggregation time, which also contains a random factor so that the recalculations are spread slightly out within the near future. The aggregation is recalculated from the values stored in the short-term buffer after the aggregation time has passed. This eliminates any duplicates. The purpose of this is to minimize the number of times we recalculate each aggregate interval. We could easily burn a lot of resources by doing this too often. It's a conscious decision never to recalculate the aggregates until a little after the aggregate intervals have ended. You can easily retrieve the raw data from the short-term buffer whenever you want to access fresh data before the lazy aggregation intervals have passed. The access pattern for the aggregation schedule queue is very update-heavy. There are a few inserts and deletes as well. The queue might grow uncomfortably large if the aggregator process isn't able to keep up with the number of scheduled aggregations. The queue length should be monitored over time as a measure of the storage system's health. Consider reducing sample rates rather than relying on lots of aggregations. I love being able to query queue lengths, worker task execution durations, information messages and exceptions from a database as part of automated health monitoring, which otherwise behaves much like a frequently running small but full-featured integration test. But beware of database connectivity exceptions and other critical server states like full disks. You might need a persistent queue just to be able to get exceptions like that into the database when it reaches operational status again. It might be a good idea to use a fully independent log analytics service instead of your regular production database. The aggregation schedule queue should work well with any reasonably fast relational or NoSQL database. It doesn't fit Cassandra or HBase, which disagrees with queues because of all the updates and deletes. An interesting thought experiment is to implement the aggregation schedule as a sorted set in Redis. That would require multiple Redis instances with failover, because Redis isn't all that good at continuously persisting state to disk. It would be possible to update the aggregates directly while using upsert statements without reading the short-term buffer, if we were certain that we would never receive duplicates. With Timescale DB or PostgreSQL, that would look like what is shown on the screen now. Cassandra and HBase doesn't allow referring to previous values when performing upserts, thus the aggregates would need to be calculated in full and not incremented on these platforms. We could have used continuous queries and retention policies to implement aggregation within Flux DB. We could have implemented aggregations using streaming API or KSQL if we were using Kafka. This would have meant creating a huge amount of tables, used a lot of computing power, and required a lot of memory to handle mem tables. It would have worked, could have become slow as the aggregate tables continue to grow, and we might have needed to scale Kafka quite a bit more than the solution based on Cassandra. The property store is responsible for organizing the equipment properties, which are usually a hierarchy, or typically include, for example, physical location, factory, building, vessel, floor, room, owner, department, equipment type, equipment ID, sensor ID, or similar properties. Time series properties such as ID used by the PLC, warm storage GUID, aggregation intervals, and storage lifetimes also belong here. The property store must support search and navigation, such as finding all warm storage GUIDs that belong to rotary speed sensors of spinning machines in a specific factory, so that you, as a next step, can retrieve historic data from the aggregate storage. Also the other way around, such as looking up the building, floor, and room for these warm storage GUIDs. Some customers have very strong relationship with this information and want to implement GUID mapping and searching on top of their own existing microservices, which already organize equipment properties. Other customers may be happy to transfer a set of properties they feel are adequate, which you can import into a simple property store, which may offer API methods for importing additional data. What is entirely certain is that all customers have different equipment property hierarchies and that they are never fully defined at the time the data starts flowing. Then it feels very good to have a central place to maintain the data, so we won't have to update the primary key to 100 million values already in the long-term storage and in the aggregate storage. You may want to send aggregation intervals with the data or have rules for detecting them, so that the data is stored correctly even if the property store doesn't contain information about the time series in advance. Then you can define the missing properties in hindsight without losing data. The API methods listed here are not required for all warm storage instances. You won't need data scientist-oriented retrieval methods if your storage needs all revolve around aggregation and displaying graphs of historical data. So consider this a mixed wish list of API methods that might go well with varying types of warm storage solutions. The insert update method is meant to be used for both ingesting sensor data into warm storage and for adding calculated values like key performance indicators from code. In general, the larger microbatch you give the insert method, the better it performs, until the memory requirements for encoding and decoding the JSON body starts to give you problems. That shouldn't happen before you're processing tens of thousands of tag items per call. It might make sense to use a queue, Kafka, or an internet-facing IoT hub MQTT server or AMQP server as a buffer in front of the insert API method. The lookup values related methods refer to a largely optional key value store. The search API methods are all about mapping metadata properties to time series GUIDs and back again, plus methods for making sure the metadata can stay current. The main purpose of warm storage is to be able to quickly retrieve the data you need, at close to the minimum resolution you need them. Note that all the query-related API endpoints are set-oriented, using an array of time series GUIDs as one of the parameters. I guess some data scientists might have a near-infinite list of magic API methods they would like to see available here. Unfortunately, this is data engineering, and will leave the magic for the data scientists to implement. The aggregator process is idling while waiting to reserve the first free aggregation time from the aggregation schedule. Any other aggregator processes running simultaneously will stay away until they acquire their own reservation, which can be when all the reservations expire, much like when you try to purchase a concert ticket at Ticketmaster. The aggregation is performed by reading time series values from the short-term buffer, writing the sums to aggregate storage, and then deleting the aggregation time together with the reservation. Then rinse and repeat. However, once you have a timer-driven process capable of performing aggregations, you can relatively easily get it to do more. For example, perform simple calculations or detect and notify of exceeded limit values. All you need is a math expression parser and a place to store the details about the expressions to be calculated. Then you'll have a rule engine. You have chosen to use JSON objects to define rules and store them in the same database as the short-term buffer. There is an ID, a name, a description, and an enable-disable flag stored with each rule. There will be API methods for defining, modifying, and deleting rules, and eventually a web front-end to edit them interactively. Our rules consist of 5 main sections for common time intervals, inputs, mathematical expressions, outputs, and alert recipients. A rule must at the bare minimum have a trigger interval that tells how often the rule should be executed. It may be appropriate to trigger a rule when receiving a specific value type. In this case, the trigger interval should be 0 minutes. The rule must also have a list of inputs, where each input element acts as a named parameters for the mathematical expressions. Each input must have a set of time series GUIDs, one or more time interval windows, and an aggregate function. The simplest time window is a single interval with a specified duration, which ends at the time the rule is specified to run. Time series are defined by a selector, which specifies filters for a number of properties in the property store. The property store queries execute when the rules are read, when starting the aggregator process. The queries result in sets of time series GUIDs and connector links that are retained until whenever the rules are reloaded. A time series selector can contain connector links, named wildcards, which are used to connect different inputs and outputs that belong together. In this example, the service location link is used to connect the sensors belonging to a pump and 2 generators, which make up a system. The measurement values from this system are complementary and are included in joint calculations and comparisons. The connector link value must exist for all time series selectors it's used with. If, for example, there is a service location with only a few generators but no pump, this service location will be excluded from the calculations. The mathematical expressions are calculated in the same order in which they are defined, and can by name refer to the time the rule is specified to run, each individual input, and already calculated expressions. The warm storage solution I'm working on now runs on .NET Core and Kubernetes. The selected mathematical expression parser, Enrico Lambda parser, uses the .NET, supports all native data types and expressions, can create and use .NET standard library objects, and supports link to objects. Incredibly powerful, still, it's safe. The rule expressions to be parsed are defined in JSON objects, stored in a local database, and are never submitted as part of IoT sensor data. All metrics are passed as JSON and treated as variables and named parameters, never as code. Therefore, no C# IoT value injection attack can occur. It's possible to run fancy code from the rules, but they require privileged access to change, and the rules themselves are run utilizing an unprivileged local user in a container on Kubernetes. Some expression names have special significance. For instance, alert, which will trigger the sending of notifications when the expression is evaluated to true. Alert message allows you to specify the message sent to the alert recipients. Message alerts can refer to connector links, which will be replaced with whatever relevant values before the messages are sent. The output section consists of a list of outputs. Each output can store a single named mathematical expression to short-term storage via a time series selector, which can refer to connection links. This means that the time series GUIDs must exist and must be retrieved from the property store in advance, if anything is to be output. Value type must also be defined in order to write to short-term storage. If you specify the expression to be all, then the specified runtime, all the inputs, and all the calculated mathematical expressions will be written to short-term storage as a JSON object. You can specify the interval and time to live to aggregate a numeric output in the usual way. If interval is specified as the number 0, the output will be written to long-term storage in addition to short-term storage. This can be combined with specifying a condition, which is a mathematical expression that must be evaluated to true for a value to be output. The alert recipients section consists of a list of recipients and the type of notification they should receive, usually email, but other integrations should be relatively easy to implement. I would like to see if this then that, and no dread. Notifications are sent to a message queue with a unique topic for each type. The message broadcasts will never block the aggregator process. It's also possible to specify a mute interval, which hopefully allows a minimum of peace and quiet between notifications. An input can have multiple time interval windows. We see an example here marked in blue. All inputs have 10 separate 1-minute intervals with 1 minute between each. That represents 10 tumbling windows. The first starts 11 minutes ago, the last 1 minute ago, offset by window lag, which is set to 1 minute. The inputs are thus retrieved as arrays with 10 aggregated values in each array. It's possible to override all of these window parameters for each input and get different sized arrays, but in this example the window parameters are the same for all inputs. Queries are used to obtain values from short-term storage, and they are combined below the surface into a single larger query using union all, which reduces the number of network delays or latency. The queries are performed asynchronously. If your short-term buffer is on a mirrored Timescale DB cluster, retrieving rule inputs will benefit from utilizing all the slave nodes, which are otherwise just replicating the master. You can also scale the short-term buffer and aggregation schedule horizontally by sharding, dedicating multiple instances to independent customers or equipment. You can use the same long-term storage and aggregate storage for all of them, as Cassandra will continue to scale linearly up to a large number of nodes. It would be feasible to retrieve rule inputs from long-term storage and aggregate storage as well, at least when you're not running the rule engine on an edge device or in a limited resource environment. Even then, you might have access to a few months' worth of carefully selected events, state changes, and aggregates. It's almost magic to have a parser that supports link and C# syntax when your mathematical expressions have arrays of floating numbers as input. Like in this example, if your inputs fetch raw data instead of aggregates, the relevant inputs will be arrays of objects. Be sure to have a short time window interval and control the number of objects by specifying limit for these kind of inputs. Here, we call a trained machine learning algorithm rather than comparing to limit values. We feed the model time-aligned historic values and tumbling window averages, sourced from a highly scalable data stream. That's pretty cool. The machine learning model is deployed to a Kubernetes pod in the form of a container and receives HTTP post requests on port 5337. We utilize the Kubernetes service selector to find the correct host address. The rule engine compounds the specified runtime, all inputs and all rule expressions calculated so far, then transmits them asynchronously as a JSON post body. When the model responds, the response is parsed as JSON and stored as if it were the result of any mathematical expression. The structure of the response object is entirely up to the model. If an exception occurs during the rule calculations, this will be logged both to the error output and to a statistics table in the short-term storage. This statistics table will contain information about the number of runs, the number of error situations, the number of timeouts, the last error message, as well as the amount of time it took to retrieve inputs and calculate expressions, with mean, max, average and sum per day. The rule statistics table says a lot about the health status of the warm storage solution and should be monitored. It's important to detect and change rules that take too long or run too often. The rule engine will have a configurable timeout for how long a rule can be allowed to run. Rules can be deactivated automatically as a result of violating this. Output works as previously described. Here we see an example of writing all inputs, intermediate calculations, and the result from the machine learning model to long-term storage as JSON, each time the model detects a deviation. Hopefully it won't be very often. The alert recipient section is unchanged from the previous rule example. You may achieve better control and improve performance by writing dedicated Python applications to calculate value-added information and detect data stream discrepancies. But rule engines are clearly capable of performing many of the tasks, even quite effortlessly, provided you are careful about the performance aspects of what you ask for. Using a rule engine like this sort of becomes the script-kiddie variant of data science for streaming. So that's it really. Don't hesitate to contact me or Knowit ObjectNet, particularly if you know of any related project leads. Thank you for watching.